Okay, welcome back to the class. So the slide showing here is an example for the problem related to a fluid jet striking a flat fan. So we go back to see the Bernoulli equations. So we know that for the Bernoulli equation, we have the pressure P1 plus the gamma Z1 plus the 2 over rho V1 squared will equal to the P2 plus the gamma Z2 plus the 2 over rho V2 squared will equal to the P3 plus the gamma Z3 plus the 2 over rho V3 squared. So first we take a look. For this problem, we assume the elevation difference for the different control surface area are quite smaller and we can neglect. So we don't have the elevation items in the Bernoulli equations. In the second, we know that all of the control surface V1, V2, and V3 are exposed on the atmosphere. So we don't have the gauge pressure items. So for the gauge pressure are equal 0. So in that way, we know that the velocity V1 will equal to the V2 and will equal to the V3. Okay? So, and the second, we base on the continuity equation. We know that the V1 A1 will equal to the V2 A2 and multiply plus the V3 A3. Okay, so the mass inflow will equal to the mass outflow. So we know that the A1 air cross-section area will equal to the A2 and the plus the A3. So you can see that the example show the different cross-section area for our problem. Okay, so the sentence just summarize and highlight some important ideas, especially for the final sentence. The jet does not cause a net force at the control surface because the pressure in the jet is atmospheric. So the gauge pressure is equal 0. Okay, so this is one exercise related to the van, and then we apply the momentum equation to the problem. So we have the water jet, okay, with the density is equal to the 1.94 slug divided the ft cubed, and it's deflected the 60 degree by a stationary fans are shown in the figures. Okay, so and the incoming jet has the speed is 100 ft per second with the diameter d is 1 inch will equal to the 1 divided 12 ft. So please find the force exerted by the jet, the force by the jet on the van. Okay, so we have the first diagram in here, and the right hand side is the momentum diagram. Okay, so we can first we write the government equation based on the momentum equation as teach before. So we can focus and then there are some spatial assumptions like the jet velocity is constant, and we neglect the gravity effect, and we don't have the pressure because all of the control surface area are exposed on the atmosphere. So the government equation we can list, we only discuss with the direction for the AKs. So for the AKs, we have the external force and with the minus directions. So you see the force is, we assume is to the left directions, and the momentum flow related to the AKs directions. We have the outflow rate. This is outflow momentum, m rate multiplied the velocity, and we need to have the project to the AKs directions. So multiply the cosine 60 degree and minus the inflow momentum, the m rate v. Okay, we minus the inflow momentum. So you know that the FAK should be equal to the n rate v. Okay, and 1 minus the cosine 60 degree. So what do we need? We need to first calculate the m rate, the mass rate, and then we can know how large the FAKs we have. Okay, so we first we compute the area. The area is we have a diameter, so it's equal to 2 over pi and the d squared. The d in here is 12 over 1 ft squared. So that will equal to, we use the calculator to compute the answer. Divided the pi, divided the 4, divided 12 second times. So that will equal to the 5.454 and the 10 minus 3 power. Unit is ft squared. Okay, and then we can compute the mass flow rate because we have the rho and we have the area and then we have the velocity. So the rho is 1.94 and the slug per ft cubed. And the area we have computed before. Okay, so I just write down in here. And the velocity is the 100 ft per second. So I use my calculator to check the answer showing here. That will equal to the 1.058 slug per second. So I convert the slug to the bomb mass. So multiply the, we need to multiply the 32.17 bomb mass. So we multiply the 32.17 to convert the slag into the bomb mass. So that will equal to the 34.038 bomb mass per second. So we can go back to see the equation showing here. We have the 34.038 the bump mass per second multiply the velocity 100 ft per second, and the 1 minus cosine 60 degree is equal to the 0.5. So we can use the calculator to compute the answer for here. So that will equal to the 171.9. But the unit is the bump mass multiply the ft second square. We need to convert the unit to the bump force. So we divided the 32.17. So the answer showing here is 52.9 bump force. So we have the X in here. This the answer Fx force is the positive. So it is satisfied. Initially we assume the Fx is go to left. So that will equal to 52.9 bump force go to left. So we move to the another direction is X. It's Y direction. Sorry. So what's the Y? The Y we also initially we assume the Y have the downward force. So we have the minus Fy downward will equal to, we only have the Y momentums related to the outflow. So we have the m rate, but the velocity direction is going down, so it's a minus v sine 60 degree. So we know that the Fy will equal to the n rate v sine 60 degree. So again, we have the mass rate 34.038, and we have the velocity 100 ft per second and the sine 60, and we need to divide the 32.17, convert the unit to the bump force. So we use the calculator to check the answer. 34.038 multiply 100 multiply sine 60 degree and divided the 32.17. So that the answer will equal to the 91.63 bump force. The answer also Fy is the positive. So and we initially assume the Fy is downward. So we know that the force in here is the 91.63 bump force. But our problem is required to answer the force by the jet on the fan. So the jet, the reaction force in here, we have the force. The jet have the force right hand side, and the upward is the fluid jet acting on the fan. So we have the positive in here is the 52.9 bump force, and the Y is the upward, so also the positive. So that you need to take care what's the problem, and we need to answer. here is we need to answer the force exerted by the jet on the van. So we need to answer the force for the blue line showing here. Okay, so this is the exercise related to the van. And then the next, we're trying to consider the different problems. For example, it's the problem related to the nozzles. Okay, so for the nozzles, the significant difference is we have the one side located in the pipe. So the side located in the pipe, so we have the additional pressure force contributed by the inner pressures. So for the problem related to the nozzle, we still need to consider one side pressure in here. So we have the pressure force on the control surface inside, and for another side, it's imposed on the air, on the atmosphere, so we don't have the pressure in here. So the gauge pressure is equal 0. So only one significant difference compared to previous fluid jet, we need to consider additional pressure force on one side. So as the sentence concludes in here, the pressure force of the magnitude where the nozzle connects to the pipe. And then sometimes for this problem, we need to apply the Bernoulli equations. If we didn't know the pressure or we didn't know the velocity at a different cross-section area. And we also need to apply the continuity equations. So that's the two equations are quite important when we solve the problem. Okay, so that's the problem exercise related to the nozzle. Okay. Okay, so the figures just show we have a nozzle, and we know that we have the inner pressure in here. So we have an inner pressure. The cross section is 1, and the outlet is cross section 2. So the inner pressure in here, we have the P1 is 3.7 10³ powers gauge pressure. Okay, and the air is forced into the atmosphere, so we don't have the gauge pressure on the cross section 2. And the nozzles, the inner diameter, the D1 is 0.06 meter, and the output diameter is 0.01 meter. The nozzle is connected to supply pipe by flange. So find the force required to hold the nozzle stationary, and we assume the air density is the 1.22 kilogram per meter cubic, and we neglect the weight of the nozzle. So idea is we hose air to the right hand side may push the nozzle to the left hand side. So what the force required in here, we first assume the force is going to right to support the nozzle stationary. So we first, for these questions, we only have the problem along the x directions. So we first write down the equations related to the momentum balance. So we have the force F, and we have the force contributed by the pressure, the inner pressure P1 A1. Okay, and then that will equal to the mass flow rate and related to the outflow momentums minus the inflow momentum. Okay, and based on the continuity, so the mass flow are the same on the cross-section area 1 and 2. So the key questions in here, we need to answer the mass flow, how large it is, and we didn't know the V1, V2 velocity. So the first, we can based on the Bernoulli continuity equation. So we have we first consider the continuity equations. So we know that the V1 A1 will equal to the V2 A2, right? And we know that the V2 will equal to the V1 and the A1 multiply the A2, and will equal to the V1 and the D1 divided the D2 square. So D1 divided the D2 is equal to the 6, and 6 square is 36 V1. Okay, so we have a relationship for the V1, V2. And the second, we have the Bernoulli equation. So we know that the P1 gauge pressure multiply the gamma Z1 multiply plus the gamma D1 and the plus the 2 over rho V1 square will equal to the P2 gauge pressure plus the gamma D2 and the plus the 2 over rho V2 square. And we don't have the P2, right? And we assume the elevation is the same at the center flow. So we know that the P1 will equal to the 2 over rho V2 square minus the V1 square. And we also know that the 2 over rho, and based on the equation 1 showing here, so we know that here the V2 can replace by the 33 square and the V1 square minus the V1 square. So that will equal to the 2 over rho V1 square is equal to the 36 square minus 1. Okay, so that the V1 square will equal to 2 times P1 and divided the rho and divided the 36 square minus 1 and over 1. So we can put the number inside. The 2 times P1 30.7 1000 par, and divided the density is 1.22, and divided the answer is 36 square minus 1 is equal to the 1295 over 1. So we can use the calculator to check the answer. To multiply 3.7 multiply 1000 divided the answer 1295 and divided 1.22. That's equal to the 4.6 8. And finally, we know that take the root answer. So we know that the V1 is equal to 2.164 meter per second. And based on the equation 1, so we know that the V2, we multiply the 36 of the V1. So the V2 is equal to a 77.91 meter square. Okay, so we can deal some item we didn't know before. So the mass rate will equal to a rho A1 V1. Okay. So the rho is 1.22 kilogram per meter cubic, and the A1 is 2 over pi. D1 is 0.06 square, the unit meter square, and the V1 is the 2.164 meter per second. So I can use the calculator to compute the answer. So 0.06 square, I first compute the A1 area, multiply the pi, and divided the 4. This is the area, multiply the density 1.22, and multiply the velocity is the 2.164. So the mass flow rate in here will equal to the 7.46 10 minus 3 power equal to a kilogram per second. So I just put all of the number go back to the momentum equation. So the F will equal to the mass rate V2 minus V1 minus the P1A1. So the mass flow rate is 7.646 10 minus 3 powers. Multiply the V2 is 77.91 minus the V1 is 2.164, and minus the P1 is 3.7 1000 par. The A1 is 2 over pi 0.06 square. So I just make the balance. So use the calculator to check the answer. So the first momentum mass flow balance, I check from the calculator. So the first item is the 0.565 Newton minus the fourth item. The fourth item, I first calculate the area. Okay. And multiply the pressure 3.7 and 1000. So that will equal to the 10.456 Newton. So finally, the force F is equal to the minus 9.89 newtons. And initially, we assume the force is going to right. But finally, we compute the answer is the minus. So that indicates the force finally is going with the force with the magnitude the force with the magnitude the 9.89, but the direction is going to left. Okay, so that's a very good example. No matter initially we assume the force directions, and we just based on the final answers is a positive or negative decided the final directions of the force. So as examples for this exercise, we initially assume the force is going to right, but finally we compute the negative answers in here. Okay, so we know that we need to offset the force direction of our initial assumptions. Okay, so that's the directions. The sentence just summarized again the idea. The direction initially assumed for the force on the force diagram is arbitrary. If the answer for the force is negative, then the force acts in the direction opposite the chosen directions. Okay, so I just concur that and summarize the sentence showing here. So another exercise is the pipe bands. So the pipe bands, as we can see, we have both sides. We have a flange and both sides inner the pipe. So we not only have the one side pressure, but also have another side include the pressure problem. So the pipe bands compared to a nozzle, the significant difference is the pipe band we have both sides need to consider the pressure force. So we have the pressure force PA and multiply the A area, and we have the PB pressure multiply the AB area. So both sides we still have the two force pressure force, and again we need to consider the Bernoulli equations and the continuity equations. Okay, so let's do the exercise and then we know what the difference. So we have the 1 meter diameter pipe. So the D is the 1 meter. Okay, and the pipe inside the fluid is oil, and the oil we have the specific gravity is 9.94, and the steady we have the steady flow rate. The discharge is equal to the 2 meter cubic per second. And the band has an angle of 30 degrees and lie in the horizontal plane. So the pipe band is just put on the horizontal plane. And the volumes of the oil is the 1.2 meter cubic. And the empty weight of the band. So we have the band weight is the 400 Newton. So assume the pressure along the center line of the band is the constant with the values of the 7.5 kilopascal. So the pressure is the 7.5 kilopascal. Gauge. So please find the force required to hold the band in place. So this problem we first divided the force into the x directions and the y directions. So we have the force diagram in here. And this right hand side is the momentum diagram. So we first consider the x directions. So what are the x direction force we have? And we initially assume the Fx is going right, and the y is we have the upward force. So only for the x direction we have the Fx the positive, and plus the Pa, the pressure force contributed by the left cross control surface. And right hand side control surface we have a deflect pressure, so we need to project to the x directions. So the minus the Pa multiply the cosine 30 degree to project to the x directions, and will equal to the momentum balance of the inflow and the outflow. So the outflow, we have the mass rate, and we have the V, and we need to project to the horizontal directions. So multiply the cosine 30 degree. This is the outflow, and then we need to minus the inflow. Okay. So the key question in here, we need to know how large the mass flow we have, and what the velocity, flow velocity. So since we have the discharge, and we know that the discharge will equal to the Q, the discharge will equal to the V multiply the area. So if we know the area, so we know the velocity is discharge divided the area, right? So we first compute the cross-section area. We have the diameter, so it's equal to 2 over pi d squared. The d is 1 meter, so we just calculate the pi divided the 4. So the area is 0.785 meters squared. And then we can put back to the equation. We have a discharge and the area, so we can compute the velocity. So the velocity is equal to 2.548 meter per second. So we have and we know that we have a discharge, so we can compute the mass rate. The mass rate is equal to a rho Q, right? And we don't have the density of the oil, but we have the specific gravity. So we know that we have the water density multiplied S 0.94 is the density of the oil, multiply the discharge is 2. So we know that the mass flow rate is equal to 180 kilogram per second. So we have the mass flow and we have a velocity. So we go back to see the momentum equations. So the Fx will equal to the mass flow rate velocity, the cosine 30 degree minus the 1, and plus the PA cosine 30 degree minus the 1. So what's the mass flow rate? In here is 180, and the velocity is the 2.548, and this is contributed by the mass flow multiplied velocity is a momentum. plus the pressure is 7.5 and 10.3 powers per, and the area is 0.785, and finally multiply the cosine 30 degree minus 1. Okay, so we can use the calculator to check the answer. The 188 multiply 2.548 plus the 75 multiply 1000 multiply 0.785 and multiply the cosine 30 degree minus 1. So that the answer is minus 8529.5 Newton. Okay, this is our the force on the x area, x directions, and we first assume the f(x) is going to right, and because the force finally is negative, so it should be going to left. Okay, so and then we can move to the another direction is the y. So we move our problem to the y directions. Okay, so what are the force along the y directions? We have the Fy positive, the upward. Okay, and we have the PA pressure can convert to the upward directions. So plus the PA multiply the sine 30 degree will equal to the momentum in here. We can project to the y direction but with the downward. So we have the mass flow rate, but the velocity is minus v sine 30 degree. So the Fy in here is equal to the minus n ray v sine 30 degree and the minus the PA sine 30 degree. So that will equal to the minus n ray v minus the PA multiply the sine 30 degree. So the mass rate in here, we know that the answer is the minus the mass rate is 1.0 and the velocity is 2.548 minus the pressure 75 10 3 powers and the area is 0.785 and then finally multiply the sine 30 degree. So I use the calculator to check the answer. The 180 multiply 2.548 minus the 75 multiply 1000 multiply the area 0.785 and multiply the sine 30 degree. Okay. So I check the answer. Wait. So we have the maybe something wrong. So I just use my calculator to double check. And the velocity 2.548 and the minus the pressure it's a 180 multiply 2.548 need to plus the 75 multiplied by 1000 multiplied by 0.785 and multiply the sine 30. Okay, so this is the minus 31832.6 the Newton. Again, we initially assumed the y direction force is upward, but right now we compute the minus answers, so the y should be going downward. Okay, and finally, because we put the pipe on the horizontal plane, so we need to overcome the weight. So we have additional direction force related to the z directions. So we have z directions. So we have a fz, and fd we initially we assume is the upward. Need to overcome the weight. The weight contributes first from the bend, the weight bend. And another weight we need to overcome is the oil weight. So we know that the oil, we have the oil volumes, and the oil volumes multiply the oil density. We'll have the mass and multiply the gravity G, and because the external force is equal to 0, so we don't have the momentum changes, so it will equal 0. So the FD will equal to WB plus the volumes, oil volume, multiply the oil density, multiply the gravity. So the WB is the 4,000 Newton plus the volume is the 1.2 meter cubic, and the density is 1000 multiplied the specific gravity 0.94 and the gravity 9.81. Okay, so we can compute the final answers. So the 1.2 multiplied 1000 multiplied 0.94 multiplied 9.81 and the plus the 4,000. So that will equal to the 15,065.7 Newton, and the positive upward to overcome the weight. Okay, so that's the very good exercise. We deal the problem with the pipe bend. So we need to consider the pressure gauge, pressure force both sides along the bend. Okay, so the table, go back to the table. We first exercise the questions related to the jet and the fan, and next we move to the nozzle and the pipe bend. And especially for this item, we need to consider the pressure force inner the pipe, or inner the pressure inside, or inner the bent pipe. So the pressure inside is very important. It provides additional force to our problems. So that's a very important. On Wednesday we will have the quiz. So the two significant questions we will have. The one is related to the fluid, the jet. Another is maybe related to the nozzle or the pipe bend. And the next class we will move to consider if the velocity is non-uniform velocity. So how can we deal with this kind of the problem? So we will use the integration operations. So previous exercise we don't use the integrations. We only assume the flow are uniform flow. So they are the constant velocity. So the next class we will practice the exercise if the problem consider the non-uniform velocity. Okay, today we may stop here and see you next week.